Just a couple of ideas and things to show at the end of this. A couple of other ways of approaching these problems. The first method here is what we call the insertion method. And so if you've got one of those problems where it says some objects are not allowed to be together. So it's a different way of approaching it. So as an example, you might recognise this question. Letters of the words between arranged in a line. How many ways can they be arranged if all the E's are separated? So the E's aren't allowed to be together. So I suppose traditionally what you do is work out, well, how many ways can I place the E's? And so I might draw a little diagram up and go, oh, okay, well, look, if there's an E in the first spot, then I could alternate and then go E, or I could go have the third E there, or I could have the third E there. So number of ways where E are in the first position 1 and position 3, I've got 3 ways I could place that third one. All right, but if I have it in the first and the fourth position, then there'd be 2 ways I could place the third one. If I had it in the first and the fifth position, and there's 1 way I could place the third one. So that's all the possibilities where there's an E in the first position. So I could have it in the second and the fourth, but then the third one could go in 2 positions. Second and the fifth, and then there's 1 way. So that now uses up all the ones where the first one's in the second position. I could have it where I've got one in the third, the fifth, and the last, and then therefore that should be the last of them. So there are 10 different ways I could place the E's. Then of course I've got to multiply it by how many other letters are there. We've got B, T, W, N. So 4 factorial, and we get our answer at 240. And possibly that's how you would have approached it. The insertion method actually sort of does it the reverse way around. Instead of looking after the restrictions first, it looks after the things that aren't restricted first. So instead of placing the E's first, we place the B, the T, the W and the N, the other 4 letters, which of course there are 4 factorial ways we could do that. But what we then say is, well, we just imagine there's a space between those letters, because that's where the E's must go. Each one must go in one of those spaces, and as long as one goes in each of those spaces, so I insert them between the other letters, no 2 will be next to each other. So alright, so 4 factorial, that's how we can arrange the B, the T, the W and the N. So I've created 5 spots, because they could go at the end of the word as well, in the beginning. So there's 5 spots I could put them. So there are the 5 spots. Well, the E's, it doesn't matter the order because they're the same. So EE is the same as EE and so on. So it's a combination. So there's 5 spaces, and I want to use how many of those spaces? 3. 5C3. And we come up with the answer, 240. So it's a different way of thinking about it for when we're separating objects. So these things can't be next to each other. So imagine if we had said exactly 2 of them are together. So now how I do it, I'd say, well, okay, I'm going to place the B, the T, the W in. I'll start off the same. But now I think of it as I've got to insert these 2 different letters. One of those letters is a double E, and one of those letters is a single E. But now they're different letters, so I don't go 5C2, I'll go 5P2, because the arrangement now would be different depending on how I place them. So 5P2, there'd be 480 ways of doing it. So that's what we call the insertion method. Okay. Now there's this other idea, what we call using separators. So if you've got a large group of objects and you want to divide it into a smaller group of objects. Okay, 3 pirates. Arr. We've got the contents of a treasure chest. So we've got 48 gold coins, which obviously would be worth a bit. 2 lead coins, not worth much at all. So the first pirate takes out coins and keeps going till he gets to a lead coin. And once he gets to a lead coin, he's got to stop. And that's his share of the treasure. Then the second pirate comes along and starts. And he keeps taking out gold coins until he gets to a lead coin. And then that's his share of the treasure. And then the third pirate gets all the coins that are left. Okay? So the question is, how many ways can we distribute these coins? An equivalent question would be, how many ways can I arrange 2 L's, the 2 lead coins, and 48 G's? And the lead coins are going to act as the separators, because that's when we're going to stop giving it to the first pirate. So it'll be 50 factorial on 48 factorial, 2 factorial. So imagine you've got 48 G's, 2 L's, so 50 letters all up. 1,225 ways of doing it. Okay. Which brings me to this HSC question. It was an extension 2 question. Interesting one. Very similar sort of question it was. How many ways can 10 identical coins be allocated to 4 different boxes? So what I want to do is have a separator so we know when we'll start putting into the next box. So like the lead coin in the first one. The lead coin told me now we'll start giving it to the second pirate. So I'm going to say, well, hang on, I'll call it an S for separator. You could have called it B for box, I suppose. You can call it any letter you like, except C for coin, I suppose. So I'm now going to have 3 separators and 10 coins, because essentially I want to end up with 4 piles of coins. And the first pile will go in one box, the second pile will go in the second box, the third pile will go in the third box, fourth pile. And so the S will be where I stop putting it in the first box and start putting it in the second box and so on. So how many ways can I arrange the 3 S's and the 10 C's? Well, 13 factorial, 3 factorial, 10 factorial. 286. Now here's the interesting thing, and you've probably noticed it on the sheet already. 1% of the state got that correct. 1%. So extension 2, you got about 3,000 people doing that paper. So about 30 got it right. 2013 paper. Hostel's got 4 vacant rooms. Each room can fit a maximum of 4 people. How many ways can 6 people be put in the 4 rooms? 6 people go in the 4 rooms, maximum of 4 people in each one. So, well, if there was no restriction, it'd be 4 to the power of 6, because each person would come along and go, I'll go in that room. And then the next person would come along and go, I'll go in that room. And the next person would come along and go, I think I'll go in that room. Or 4 to the power of 6. That's if there was no restrictions. So that's the total number of ways. Now the reason I've done that is because I think it's going to be easier to work out the number of ways things can't happen and take away from the total number. So what can't happen? Well, we can't have all 6 in one room. So number of ways, well, we choose which room all 6 are going to go into. 4C1. So there's 4 different ways all 6 could go in one room. Okay. What else can't happen? 5 goes into one room and then someone else will just be in another room. That can't happen. So all right. 5 in a room. So we got to choose which room's going to have the 5 in it. 4C1. But now we've got to choose which of the 5 people, which 5 of the 6 people are going to go in that room. 6C5. That leaves one person by themselves going, you don't want me to be with them. It's all right, I've got 3 rooms to choose from. So 3C1, and we get 72. So there are all the ways things can't happen. Subtract, you get 4,020. And again, you might have already read off the sheet about the interesting thing with this one. A few more got this one right. 15% got it right. Problem was it was multiple choice. So when you think about it, even if you random guess, you'd expect 25% to get it right. But no. Only 15% got that one right. Now, this last bit here, I guess what I want to do is show you how a topic which doesn't seem to be related to algebra can be used for algebra. And that's expanding parentheses out. We can actually use this idea of permutations So we know a plus b all squared is a squared plus 2ab plus b squared. Why is it that? Why are those numbers? Why is it 1a squared, 2ab and b squared? Yeah, okay, if we expanded it out we can see why. But there actually is another reason why. Here, a plus b squared. What I'm going to have, every time you multiply, you choose one letter out of one parenthesis and one letter out of another parenthesis. So the question is, what are the different things you could have? I could choose an A and an A. I could choose a B and a B. And the other possibility is... So, what are all the different ways we could write the A and the B down? So I could write them as A squared or B squared. In other words, two of the same letter, or I could have different letters. So now the question becomes, how many ways can I arrange two A's? One. How many ways can I arrange A and B? Two, or more importantly, 2 factorial. And that's why it's a squared plus b squared plus 2ab, but we write it a different way. Now using that idea, then we should be able to expand out anything squared, because it will be exactly the same idea. I could, out of one parenthesis, either choose an A and an A, or a B and a B, or a C and a C. In other words, I could choose the same letter twice. One way of doing that, choose the same letter. Or I could choose two different letters. So all the different possible pairings, there'll be two of those. So A plus B cubed. A plus B cubed. So we've got to think about it. What are all the... We've now got 3 sets of parentheses. Each one has A and B in it. We're going to pull out 3 sets of pronumerals. So we could have all of them being the same. So we get A cubed, B cubed. Okay. We could have one of one letter and 2 of the other. So either AB squared or A squared B. There's no other possibility we could have. So now the question is, how many ways does that happen? How many ways could I write A? 1. So how many ways? 1. How many ways could I write A? Well, let's take the first one, A, B, B. How many ways could I arrange that?
30.
Well, yes, 3 factorial over 2 factorial, because you've got 2 B's there, which does turn out to be 3. And so there's our expansion for A plus B all cubed. Written slightly different. But we've got A cubed plus B cubed plus 3 lots of A squared B and AB squared. So if we push that idea a little bit further, if I had A plus B plus C all cubed, so now I've got A plus B plus C times A plus B plus C plus A plus B times C. So what are all the possibilities I could have now? So yet again, yes, I could have A cubed, B cubed, C cubed, 3 of the same. I could still have the A squared B, 2 of one, 1 of the other. But now there's a third possibility. I could have 1 of each of the pronumerals. What will the coefficients be? Same question. How many ways can I arrange A? 1. How many ways could I arrange 2 A's and a B? So, same as that. How many ways could I arrange A, B, C? 3 factorial. So the expansion of A plus B plus C all cubed, A cubed plus B cubed plus C cubed, 3 lots of all the pairings there, and 6 lots of A, B, C. Let's push this further. If I had A plus B to the power of 4, so now we've got A plus B times A plus B times A plus B times A plus B. What are all the possibilities? I could have picked 4 of the same letter. I could have picked 3 of the same letter and then 1 of the other ones. I could pick 2 of one letter, 2 of another letter. How many ways can it happen? How many ways could I go A? 1. How many ways with A, B, B, B? 4 factorial and 3 factorial. How many ways A, B, B? So therefore, the expansion is a to the power of 4 plus b to the power of 4, 4 lots of ab cubed plus a cubed b, and 6 lots of a squared b squared. We're having fun yet, or what? So, just for the heck of it, imagine we had a plus b plus c plus d all to the power of 6. So, a plus b plus c plus d, 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 a plus b plus c plus d. We're going to take one letter out of each of those parentheses. What are all the possibilities? Well, I could have all 6 of them being the same, and yes, there's one way of doing that. I could have 5 of them being the same and 1 being different. And that would be 6 factorial and 5 factorial. I could have 4 being the same and then 2 of another one. And that would be 6 factorial and 3 factorial, 2 factorial. I could have 3 of one, 3 of another. 6 factorial, 3 factorial, 3 factorial. We could have had 4 of one, 1 of another, then 1 of another. 6 factorial and 4 factorial. We could have 3 of one, 2 of another, 1 of another. We could have 2 of one, 2 of another, 2 of another. Okay? And of course we could have 3 of one, 1 of another, 1 of another, and 1 of another. Are we finished? No, we're not, because we could have 2 of one, 2 of another, 1 of another, 1 of another. Whoops, I didn't actually simplify that. But there you go. There is our expansion of a plus b plus c plus d all to the power of 6. Wouldn't that be a nice question for the test? But, you know, it's just the same idea, and we're just translating it through to a higher order question. As fun as that. Anyway, don't panic. We're not going to ask that sort of question. It's just a way, as I say, showing you how topics in maths can be used in other areas in maths that you might not have expected. All right.